Good morning, everybody, and welcome to Physics 101. Today is Wednesday, October 19th. We are in week 7. We started this week on Monday, basically when we talked about gravity and the law of gravity, namely Newton's contribution to the law of gravity. As a matter of fact, he's the one who started it all. And we saw basically that any two masses, regardless of how big and small they are, attract one another. I want to remind you of this key point because in about 2 weeks, we're going to start electricity and we're going to see something similar between charges. And charges, on the other hand, not always attract. Okay, sometimes charges repel one another. So the force of gravity, it's always attractive. Two masses always attract one another. And this force is proportional to the mass, of course. The more mass you have, the more attractive force you have. And that's why we get tired, because of the fact that we are constantly interacting with Earth. And Earth is a very, very massive object. It's about 6 × 10⁻24 kilograms versus our masses, which is less than 100 kilograms on average. So this is an attractive force, and it always applies between any two massive objects. The other contribution also, the other factor that plays a role in here is the distance. Faraway objects interact less than nearby objects. Nearby objects with given masses attract more than objects at faraway distances. And how is that relates? It relates to the square of the distance. Two objects, if they're a meter apart, they attract one another with a force. It doesn't matter what that force is. If you double the distance, that same force drops by a factor of 4, because the square of 2 is 4. And when you divide by the square of 2, that means the 4 drops by a factor of 4. Similarly, if you have two objects sitting at a given point and they're attracting one another with a given gravitational force, if you halve the distance between them, in that case, the force quadruple, because again, it's inversely proportional, meaning that if you bring them closer, the force gets bigger. And how big it's going to go? It's going to go big as far as the square of the distance if you bring them closer. How big it's going to go when you pull them apart? It's going to drop by the square again of that distance, and how much increase in distance you have. Obviously, if you triple the distance, the force then shrinks by a factor of 1/9. Because again, you're dividing by the square of 3, and the square of 3 is 9. So this is basically the discussion that we have from there. A lot of applications, of course, come to play. One of them, actually, the whole reason why Mr. Newton basically thought of the problem and came up with this law was to explain Kepler's laws. So let me share with you briefly, because we're not going to get into angular momentum in this class, but we're going to get into the linear momentum, which is part of the discussion today. So let me explain the correlation, because I think historically it's a critical piece of connection. And also it helps you understand the stars and how they work. So let me see if I can get this whiteboard in here and open. Hopefully you guys can see it. So prior to Mr. Newton, Mr. Kepler came up with 3 laws. And the 3 laws basically in a nutshell are planets as they go around the sun, because at that point the assumption was planets go around the sun. Actually, it's a fact. Can I put an N in here? Okay, this is the sun, this is a planet, and this is another planet. The first argument that Mr. Kepler argued is that this paths of these planets as they go around the sun, they go in ellipses. The second law that Mr. Kepler has found, so this is Kepler's laws. Okay, so the second law basically that Mr. Kepler has found is that planets sweep equal areas with equal amounts of times. These 2 laws, law number 1, so equal areas. So the first law is that the paths are ellipses or elliptical paths, elliptical paths. Okay, the second law is that equal areas are swept at equal amounts of time. Equal times. These two laws are related to a concept that unfortunately we don't really have time to explore in this class, but the concept is called angular momentum. I'll probably briefly talk about it once we talk about the linear momentum, which is required for this class. And then the first law actually has to do with the direction because of this quantity of the angular momentum, because the angular momentum is actually a vector. Okay. And the second law has to do with the quantity of the same number, same thing. So which is really the size of this same quantity. So that's basically the two laws. And the third law is actually related to something else. And the third law of Kepler basically says that the square of the time. So sometimes since it's a period, we use the letter T. It's the same things, but he used the letter P. So we're going to stick with the letter T, is basically equal to how far on average the planet is from the star, from the sun in this case, in general. So that's basically cubed. So you have to cube this value. So this is basically what this law is. So why is this thing here? Wait. So this is basically what Kepler's law is. So let me briefly discuss this. I know I didn't discuss that last time. So we did the circular motion, an object going in a circle. Granted that this is not circular, they're elliptical, but as I said last time, they're very, very close from circular paths in the sense their eccentricity is very, very low. In other words, the two focal points are almost on the same point, which is the center of the circle. So I'm going to use the law that we discovered last time. This is basically the mass times the centripetal acceleration of the planet goes around the sun, and v squared over r is the speed of the planet divided by r times the mass of the planet, is given by the force that Mr. Newton has argued, m times the mass of the sun divided by the distance squared. Okay, so r is the distance between the planets and the sun. The velocity of the planet is equal to the circumference of the circle it goes around, which is 2 pi times the radius, divided by the time it goes around it. So if I combine these two, first of all, the mass of the planet cancels. And that's very, very important consequence because it's the same quantity on both sides. So I can divide by it and it goes away. Now, what I'm left with on one side is the velocity squared of the planet, which is 4 pi squared times r squared divided by t squared. So it's going to be 4 pi squared times r squared divided by the period squared, the same p that Mr. Kepler has used, is equal to, of course, g, that's a constant that Mr. Newton has found, g times the mass of the sun divided by r squared. Remember, the mass of the planet has been canceled, so that's why I'm not writing it on both sides. Divided by, did I forget the term? Divided by r, because this is just v squared. This is just v squared. They have to be divided by r to make it as a centripetal acceleration. Obviously, this r squared and this r cancel from numerator to denominator, and I will have an r here by itself. And then I will have t squared. So, and I need to move t squared to the other side so that I can write it similar to the Kepler's laws. So t squared. And in the same time, I'm going to move r squared to the other side, which means it's going to come to the numerator. But I already have an r left from that cancellation. Remember, I have an r squared divided by r. So I have an r left in here times r squared. That's an r cubed. And the rest is just constant. So I have a 4 pi squared times r cubed. So it's 4 pi squared divided by g, which is at constant 6.67 times 10 to the negative 11 times the mass of the sun. So time divided by gm. So here is the thing. Here is why this is a very, very important contribution that Mr. Newton has done. He not only found the same law that Kepler has found. Kepler has found it just by observing basically the path of the planets around the sun, and he argued that the square of the period is proportional to the cube of the distance on average. And that's the same thing. The square of the planet, of the period of the planet, is proportional to how far it is cubed in this case, provided that the path is very close from circular path. This conclusion actually turns out to be true even for an actual elliptical path. Now, Mr. Kepler, basically, all he said in here is that, look, these are the equal, granted that T is in years and A is in astronomical units. But that's true, because the Earth is actually the candle. The Earth is is the one that we're comparing stuff with respect of it. So T is 1 squared, that's 1. 1 year that is squared, that's 1. And the distance is astronomical unit. That's how far the Earth is from the sun on average. So you cube 1, which is 1 times 1 times 1, and you end up with 1 equal to 1. Then you compare all of the other planets to the standard, in this case, Earth, and the period will be higher for the case of Venus, for example, and for the case of, the period is higher actually for the case of Mars and Jupiter, because they take a long time to go around the sun versus the Earth. And how far they are also is greater. And the two numbers actually increase accordingly. For the case of Jupiter, for example, it takes about 12 years to go once around the sun. So it's 12 squared, roughly 12, it's not exactly 12, is equal to about 5.2 cubed. Okay, this is rough. I mean, I'm giving you a rough estimate in here. It's not exactly 12 years. So this is about 144, about, not exactly. This is also about 144. In other words, instead of saying 1 is equal to 1, now we're saying basically that in this situation in here, 144 equals to about 144. 140 is about 140. Because if you cube the numbers, that's how they turn out to be. So the point being in here is this is actually in years, and this is in years, and this is in astronomical units. But here is the deal: Mr. Kepler, Mr. Newton has found exactly what that number is. So not only the law is true, if you push T instead of in seconds and R instead of meters to T in years, and R is actually in astronomical units, this number turned out to be exactly 1. But if you put the seconds in here, and if you put in here the meters, this number turned out to be just in the constant in here, 4 pi squared, divided by G, which is a number, times the mass of the sun. So in a sense, this is the weight of the mass of the sun. That's how you weigh it. Okay? Or the mass, actually, not the weight. Mass of the sun. So that is basically, in a nutshell, what this thing is. So Mr. Newton went a step further. He was able to do stuff with it, that this law is more general, okay? Another point from that last time that I didn't discuss, and hopefully you guys have caught up on it, on Earth, the weight is mg, just above the surface, where this g, this is the weight of any object of mass m. So now we're talking about an apple, or you and I, or a chair, or a car, or whatever the object that you're thinking about, as long as it's just above the surface of the ground, basically maybe 100 meters, 1,000 meters, kilometers if you want, or 5 centimeters, it's still the same thing. So it's nothing compared to the radius of the Earth. Remember, this must be equal to, given by the law of Newton, which is g times the mass of the Earth now, since we're dealing with the Earth, divided by mainly how big the radius of the Earth squared. This number, and I think we did it last time, we argued that this is exactly 9.8 meter per second squared. Okay, so that works fine on Earth in here. If you go to the moon, for example, and you would want to weigh yourself, you're going to do the g for the moon, not the g for the Earth. It's not going to be 9.8, it's going to be something else. So it's going to be your mass. That doesn't change. So if astronauts, when they went to the moon, their mass stayed the same. Basically, how much stuff they have inside. Basically, their body, molecules, and all kinds of things that makes them. Okay? So that doesn't change, but the G changes. It's the same G, but now instead of the mass of the Earth, so this is the Earth, now we're talking about the mass of the moon, which is different, divided by the mass of the radius of the moon now, which is different. So G now changes from planet to planet to planet to planet, which means that the weight changes from planet to planet to planet to planet. So if you are on Mars, it's different value. Again, the mass of Mars is a lot less than that of the Earth. And also the radius of Mars is a lot less than that of the Earth. So you work out the numbers and you're going to find a different value for G on Mars. As a matter of fact, even here on Earth, it changes. In San Bernardino, it's not exactly 9.8. It's actually slightly less than 9.8, 9.79 or something like that. So because again, it depends on elevations, it depends on how far you are from the equator, because the Earth has a shape that is not exactly spherical. It's a little bit wider on the equator than between the North Pole and the South Pole. So that is some of the features of the Earth, in addition to the fact that the density is not exactly uniform all the way throughout. So that also plays a role. So that's basically, in a nutshell, the discussion from last week. So today's topic, though, okay, how do I get rid of this? Export as PDF. Okay, right now it's exported. So let me close it now. Now move it to the trash. Yes. Okay. Anyway, so the point being in here is that this is the discussion from the previous unit from Monday. So this is a build up on those concepts. Now we come to the concept of momentum, and I already mentioned that there is a version of momentum that has to do with the motion along the rotation, and that is called angular momentum. So we're not going to explore as much as the angular momentum as we would do for the linear momentum. So let me see if I can get this in here ready. So I'm going to use a different actually notes in here. So let me share my notes in here. That's actually easier. Anyway, let me pick up a thicker pen. So anyway, basically at this point, we were dealing with a fixed mass. So mass really does not change. Mass is fixed. So in that situation, you say F is equal to ma. You have to understand that the acceleration is a vector and the force also is a vector. So all along, if you apply more force to an object than what you did in the beginning, so this is a little force, and this is more force, then the result is, in the first case, you probably will get an acceleration that is this much. Now you're going to get a bigger acceleration because, so this is F little, this is how much you're going to get. Now we're going to really get more acceleration because the force all of a sudden is more. So F more over whatever the mass is. But think of the following scenario where this problem becomes an issue. If you have two objects, or the same object, okay, so the same objects, and it's sitting minding its own business, and all of a sudden something happened inside so that it broke into two pieces. One piece went this way and the other one went the opposite direction. So this flew this way and this flew this way. So the mass is not fixed now. So the mass that you started with, part of it went in here. So this is part one and this is part two. So that when you add these two masses is the original mass that you started with. So this is a case of an explosion. Similarly, you could have an implosion. You could have two cars, for example, on a track, for example, train track. So one of them is coming this way and another one is coming from the opposite direction, and they fuse and they become a single car at the end of the day. Basically, now they're one big train, okay? So the original car has a mass m1, the second one has an mass m2. I know they look, I mean, if you go to the train track, they look the same size, but one of them may be loaded. So one of them has a bunch of stuff on it, and the other one is empty. So the two masses are not necessarily the same, depending on how much stuff is in them. At the end of the day, now they have a new mass, which is the sum of the two masses. So this is the before, and this is after. This is the before in the first case. You had one object before. So this is before. And this is the after. After the explosion, now we have this scenario. This is a case of an implosion where you have two objects, and then after they implosion, they basically come together. Okay, they attach and they become, in this case, one piece. Okay, so now when they were separate, you have for each and every one of them its own forces times equal to its mass times its own acceleration, and this one is also the same thing. It has its own forces equals to its mass times its own acceleration. But now they're only one system, which is the entire mass times whatever acceleration one has, the other one must, because of the fact that they're linked. And in the first scenario in here, they had initially the same acceleration. The two people actually, they were not separated. And now all of a sudden they fly in every which way. Each one will carry with it its force time equal to basically its mass times its own acceleration. And the other one will have a bunch of forces that may or may not be the same, equal to its mass, which is different, not necessarily the first one, times its own acceleration, which may or may not be the same. So in this scenario, this is basically the case that we have in here. So here is the deal. When we said F equals to ma, we were really thinking the rate at which the velocity changes with time. Okay, but if the mass is actually changing with time, I'm going to throw it in this expression, and it becomes the rate at which both the mass and the velocity change with time. Okay, in this combination, because this is a product. This is the origins of the momentum. So the momentum, by definition, is P, which is a vector, by the way, because the velocity also is a vector, is equal to mv. So this is the momentum vector. Okay. Note that this is actually a linear momentum, since I started talking earlier about when we were doing gravity about angular momentum. This is a linear momentum, meaning an object moving in one direction with a given mass, with a given velocity, will have a momentum that is a scale version of the velocity, no more. So it's mass times velocity. So the momentum is a scaled velocity with the scaling factor being the mass itself. That's basically what that is. So here is what that means, okay? It's a big deal, okay? Let's say, for example, I have a ball, doesn't matter what type, traveling with a speed of 5 meters per second. So that you know, a meter is 1,000th of a kilometer, and a second is 1/3600th of an hour, because in 1 hour, I have 60 minutes, and in 1 minute, I have 60 seconds. So this is 3,600 seconds. So 5 meters per second is 1,000th of a kilometer. And a second, which is, so it's an hour. So it's 3,600ths of a second. So now I'm doing kilometers per hour because I did the conversion. So obviously 1,000 when you divide it by 3,600 when divided by 1,000, 3.6 times 5, 5.3 times. It's less than 20 anyway. It's less than 20 miles, 20 kilometers per hour, less. I mean, if you want to have the exact number, it should be more than 15, but less than 20, because 5 times 3 is 15. And 5 times 4 is 20, so it's a number in between them. I'm not going to generously say it's 18. So let's do it quickly in here. 5, oh, here is the keyboard, sorry. 5 times 3.6. It's exactly 18. So it's going by 18 kilometers per hour, okay? If you're wondering how many miles per hour that is, that's about 10 miles per hour, slightly less, slightly more than 10 miles per hour, because again, 1 mile is 1.6, so 18 divided by 1.6, so it's 11.2 miles, 11, slightly over 11 miles per hour. So that's how fast a ball that I gave it 5 meters per second. Now, how much momentum it's carrying with it, though? Let's, for the sake of argument, give it a mass, probably about a pound, maybe. So it's about 500 grams, which is half a kilogram. So if you're wondering how much momentum this mass in here is, this ball in here is traveling, so it's going to have P, which is 0.5 times 5, and that is 2.5 kilogram meter per second. So this is how we find the momentum. The direction of this momentum is in the same direction of the velocity. So how much force would I really require to stop it? Let's say, for example, in 1 second. In 1 second, I would need, so remember, it was this much. So when it stops, its velocity is 0. And since its velocity is 0, its momentum is 0. And it just said that the force then is the change in momentum over time. So if it takes 1 second to stop it, then in this case, the force required to stop this ball is going to be at the end. Remember, delta is the change over delta t, and delta t is exactly 1 second. So we want to stop it in 1 second. So this is delta of mv. So the last mv is 0, and the initial one is equal to 2.5 kilogram meter per second divided by 1 second. So if one takes 1 second to stop it, then it requires a force that is negative 2.5 kilogram meter per second squared. Remember, second and a second becomes second squared. This is in Newton. So the negative sign in here means that we're bringing it to stop. Okay, so this is actually in Newton. So it requires 2.5 Newton to stop it. No big deal. I mean, it's not really hard. 2.5 Newton is hardly anything that you can manage. Okay, you can stop it. Obviously, if it's moving faster and you would want to stop it in 1 second, the initial momentum will be higher. So let's say, for example, it's coming at 10 meters per second, which is about 22 miles per hour. This is not even a fast ball, by the way. It's a very, very soft throw. Okay, so fast balls usually are around 90 miles per hour. So they're far more. So it's about 9 times faster. So they're coming at 25 meters. It's more. 9 times 5 is about 25 meters per second. So they are coming even more velocity. Okay, professional baseball players, of course, we're talking. In that case, it will require 9 times as much force. Okay, so it requires more force to stop that one. So straight throw coming straight to the pitcher, to the catcher. I'm sorry. So the point being in here, you have an understanding, and there's no big deal with it. Here is the problem. I'm going to take the same speed of 5 meters per second, but instead of having that being for a half a kilogram ball, we're going to take it for a car, and a car weighs about 1,000 kilograms. Can we stop it? How much force would we require to stop it? Obviously, we should not use our hands to stop it. We cannot use. There is not enough baseball, basically a glove to stop it. Okay, so even with this speed, which is not much, 5 meters per second is 11 miles per hour. Okay, so this is basically barely a car that is rolling on the road. Okay, so in this case, what happened in this scenario is the momentum again is 1,000 times 5. It's a 5,000 times kilogram meter per second. And if it takes 1 second to stop this one, so at the end it's 0. The initial one is 5,000 kilogram per meter. So all you have to do is to find the momentum as you multiply mass times velocity in 1 second. So the force required to stop a car in this case is going to be even higher, because it's going to be negative 5,000 newtons. Again, kilogram meter per second is a kilogram, is a Newton. So 5,000 newtons versus 2.5 Newton. So it requires a lot of force. Okay, that force cannot be supplied by your gloves. It has to be supplied by the brakes, okay, of the car. So it has to be supplied by the brakes of the car. And this is not a big force, as a matter of fact, because the car is moving at 11 miles per hour. Imagine if the car is going 60 miles per hour. Well, in that scenario, you're talking about 12 times more than this one. So the brakes now, they have to supply far, far, far more force, about 60,000 newtons or something. And that is even, that's why the brakes actually work very hard to stop vehicles. So granted that the time also plays a role. If you brake the same car over an extended period of time, now That's actually a more desirable way. So again, this is basically the concept of momentum. So it's mass velocity combination. I mean, a bullet that is extremely light can hit a big animal and bring it down compared to that animal which has a more massive object mass. Okay, so again, the momentum is a combination of both mass and velocity. Okay, so that is really the point that that needs to be taken from this whole discussion. Okay, now to go back into an example that has that you guys have it in the book, and it's really an interesting example. Imagine with me that you have a 5 kilograms, so I'm going to change the number slightly, 5 kilogram mass moving at 1 meter per second this way, and you have a 2 kilogram mass. I'm changing the number slightly on the workout, moving at, let's say, for example, 5 meters per second. Okay. And after they collide, so they're separate, they're completely distinguishable now, these two masses. Okay. They do so in such a way, this one, for example, will continue moving or change direction, for example, to 1 meter per second this way. How fast is the other mass is? How fast is the 2 kilogram? So the 5 kilogram changes direction. And now at the end of the collisions, how fast is this one is moving? Okay, before getting to the collisions and stuff like that, let's talk about some critical pieces in here. When I have two masses and there are no external forces, the momentum before is the same thing as the momentum after. You're asking, why is that? Very simply, because if I take the entire system as just one system, that system, granted, as I said in here, no external forces. I mean, the only forces at play in this case are internal forces. In other words, one mass pushes on the other one pushes back on it. And that is internal forces for the entire system. And those internal forces obey the third law of Newton. So basically, they cancel each other. So internal forces cancel. So in this scenario, the overall system will have an initial momentum that is equal to the sum of the momenta before. So the first mass times its velocity plus the second mass times its own velocity. This is the before. So the entire system now. Now, the entire system will have a momentum after, which I'm going to call after, will be its own mass, the mass of the first one times the new velocity of the second one. So I'm going to put a prime in here just to distinguish it from the first one. And the second mass will be moving with a different velocity, not necessarily equal to the initial velocity. That's why I put a prime in there. The change in momentum over time during the collision must be equal to the external forces. That's what the law of Newton says in this case. Also, all the forces. So the forces must be equal to the change in momentum. So the momentum at the end for the entire system over a finite amount of time. So what is that change? It's the momentum after minus the momentum before over time. The last time was changed, we tracked to the initial time we changed. So before and after, basically, how long did this collision last? That's basically what that stands for. Now, because the internal forces cancel, due to the third law of Newton, every action has an equal and opposite reaction as long as these two particles are interacting. And if external forces are zero by assumption, then this must be zero. Since this is zero, then the momentum after must be the momentum before. Namely, the numerator must be zero, because this collision will take some time to occur. So the denominator is finite. It's a number, like 1 second or 2 seconds or 3 seconds, doesn't matter. So in this case, the change in momentum is 0, so that the sum of the forces are 0, because the internal forces, they cancel under any circumstance, always canceling, and then there are no external forces, because that's the assumption. Nobody is pushing one car over the others. Okay, nobody's pushing one object over the other. So this law here, which says basically under these conditions, if there are no external forces, the momentum after is the same as the momentum before. So this is the law of conservation of momentum. This is a big deal, by the way. This is one of the most important laws in nature. Actually, this is more important than even Newton's laws of motion. Okay, just to tell you, how important this. I mean, yes, we derived it from F equals to ma. Basically, we argued it from F equals to ma, but the law actually goes beyond that. So this one actually applies even in scenarios where the law of Newton fails. Okay, the laws of Newton's laws fail, and Newton's laws do fail. Actually, they do, and I know we said that they do apply in everyday experience, and that's true. But for the case of the objects that are moving super fast, where relativity is needed, Newton's laws would not work. Or for the tiny objects like electrons and protons, where basically defining their position doesn't make much sense, so let alone their velocity or acceleration. So in that scenario, also Newton's laws do not apply. But in both of these cases, this law still holds. The momentum is always conserved if there are no external forces. That's why this is actually a very, very important law. Okay, as long as no external forces, as I said before. So this should help us understand problems like this one. This is a typical collision now problem. So all I have to do now, choose a direction. Let's say, for example, this direction is positive, just because the last object in here, the more massive object, is moving this way. Then in this scenario in here, initially it was moving with a negative speed, so it has -5 times, that's its mass, times 1. This one is positive, moving in the positive direction, so it has a positive 2 kilogram times 5. This must be equal to the momentum after. Well, the momentum after of the 5 is positive, so it's 5 times 1. And the momentum of this one is a 2 kilogram times, oh, we're going to get 0. Yeah, that's fine. Okay, times its velocity, which we don't know. Times its velocity, which we don't know. So I'm taking it, it's going to be moving this one. If the number turned out to be negative, it's actually moving in the opposite direction. So -5 times 1, that's -5. 5 times 2, that's 10. So the sum of these two is actually equal to 5, because -5 plus 10 is 5. And this is 5. So I have 5 is equal to, this is, by the way, kilogram meter per second. Those are the units everywhere in here. So this is equal to 5 again, kilogram meter per second, plus 2 times the velocity, because it has a 2 kilogram, the velocity of this object, which we don't know. The 5 cancels the 5, and in here I have 0 equal to twice the velocity of this object. So this object actually comes to a standstill. It's not going to move. Okay. So one of them is coming 1 meter per second, it's more massive. And the other one is coming 5 meters per second, zooming, but it has less mass. Once they collide, the first one that was moving, this one changes direction, goes back from where it came from with the same speed. So its momentum really, in magnitude, did not change. But since it has a vector, it really did change. And the change is twice as much as the initial momentum, because it went from a 5 kilogram meter per second this way to a 5 kilogram meter per second in the opposite direction. So it takes a 5 kilogram meter per second to stop it, and another 5 kilogram meter per second to move it in the opposite direction. So it takes twice. Now the initial one came with twice as much as momentum than the first one, exactly what the doctor needed to impart that momentum to it so that it changes direction and moves in the opposite direction with the same momentum it came with. Now the first one, the second one, I'm sorry, the 2 kilogram, does not have any momentum to do with anything, since it did not basically do so. That's it. Okay. Had it come with 4 meters per second in this case, not 5 meters per second, that too will have to actually is going to move. So if its momentum is actually 4, is going to move in the same direction in this case, okay, albeit slower, and so on and so forth. At the end, the momentum is conserved. This is a case of a collision of two objects in here, and I know you have several examples in the book, so please read them and do them. And if you guys have any questions, please do not hesitate, okay? There are two types of collisions. There are elastic collisions and inelastic collisions. The distinction between them is kinetic energy. In the case of elastic collisions, the kinetic energy before is the same as the kinetic energy after. So before is the same as after. So the kinetic energy doesn't change. In the case of an elastic collision, the kinetic energy before is not the same as the kinetic energy after. That's basically in a nutshell, okay? Now, this is an ideal situation. You will never have kinetic energy before equal to kinetic energy after. So for a bouncing ball, for example, as it hits the ground, when it bounces, if the collision with the ground is elastic, so it should really bounce back with the same velocity as it impacted the ground. So then it should really go back to its original height and keep on doing this forever and ever. And that is not true. In our daily experience, if you drop a ball, for example, a basketball on the floor, it's going, and you drop it from a certain height, it's going to deform upon impact. And then if you actually look with a microscope to the ground, actually the ground also deforms too. So part of that energy that it had, the kinetic energy as it hit the ground, has been converted to those two forms of energy, the deformation of the ball in the ground. In addition to sound that you can hear when the ball hits the ground. So that is another form of energy that is also lost to that effect. And there is also a friction, and there is all kinds of phenomenon involved with it, with the air. So when it bounces back after it's restored back to its own shape, it's going to bounce back to a lower level than what it started with. And it's going to bounce back again to the ground and go through the same process. The next time it's not going to reach the first height, and the third time is going to probably at the end it's going to start basically until it gets to the ground forever, it sits in the ground. So this is a case of a more realistic collision where the impact in this case is actually inelastic. So inelastic collisions are actually more common than, are actually more practical than elastic collisions. But there is a case of inelastic collisions that are also ideal in a sense that you have two objects, for example, you throw them to one another and there is a Velcro in here and there is a Velcro in here. And you do this, and once they attach, you would want to minimize all of those things, namely the sound on all of the things. So part of the energy, yes, is imparted to the Velcro to attach. And for this case in here, this is an ideal or very close from it to an ideal collision. So they fuse. If the two objects fuse, then in this situation, we're going to treat it as an ideal inelastic collisions where the momentum before. So remember, I have two objects. The first one is a mass m1, the second velocity v1, and the second one is m2 times the velocity v2. Now they're combined, they fused, so they're only one object with a given mass, the sum of the two, times the velocity of the common, the two of them, since they're fused now, okay? So this is easy, okay? Now for the case of in elastic collisions, we could do this on the for the case of elastic collisions, we could do that usually with cars on rails, small cars basically, with magnets, okay? So imagine that this is a north pole of a magnet and this is a north pole or a south pole, doesn't matter. Okay, similar magnets, okay? So you push them against one another and they're coming, and the two similar magnets will repel one another. So before impact, in this case, the force of the force of the magnetic force actually will force them so that they don't touch and they come back again. No sound is produced, no heat is produced, and no other forms of losses. So this minimizes also those effects. So this is close from the ideal. Okay, and this one also is close from the ideal, where the two objects in the area, they come in and they fuse and they stop actually. Okay, so they stop after they fuse. So again, those are some extreme cases, but in general, inelastic collisions are the most common ones in here in this case. Okay, so the big deal of this chapter is actually the angular momentum and the fact that, I'm sorry, linear momentum, and the fact that it's proportional to the mass times velocity. There is another key concept in here, and let me illustrate this concept in here that is going to come in handy. Remember I said the force is the change in momentum, because now mv is just a momentum divided by time. I could multiply both sides of this equation by delta t. On this side, delta t will cancel, and here I will have a delta t. Usually we write it in front of the vector. I mean, after the vector. So what happened in this case, the change in momentum for any object or combination of objects is equal to the force times the time it takes for the force to apply. And this is a very important concept because, first of all, this concept is called an impulse. So this is another concept. And this is the change in momentum. So basically what's going on in this case, if the force is given time, which is in this case delta t, it's going to change the momentum of an object or a system. So if a force is allowed time, it will change the momentum of the system by imparting it with an impulse. So how much is the impulse? The symbol for impulse, by the way, is J, so that you guys, the letter J is force times delta t. That's basically what's going on. So think about it this way. You have, for example, a cannon. And you have another cannon in here. Oops, I did not mean to do that. Another cannon in here. One of them is a short barrel, and one of them is a long barrel. And you have the same amount, for example, of powder, okay? And you have a cannonball in here, and you have the same thing, the same cannonball, both of them the same masses. Well, the cannonball in here is going to take more time under the effects of the force that results from the explosion of that powder to exit the cannonball, the cannon, I'm sorry. And the cannonball in here, the second case in here, it will take less time under the same conditions, namely the same amount of powder, to exit the barrel. So in this case, the force is allowed more time to change the momentum. The cannonball was not moving. At the end, is going to emerge with a big momentum times velocity vector. Okay. Whereas in this scenario in here, it's going to be, so this is big. In this case is here is going to emerge with a tiny, basically, velocity or tiny momentum at the end of the day, because the impulse in this case is higher, and the impulse in this case is lower. Okay. So this is one example. Let me give you another example to illustrate the point in here, okay? So the time plays a role. let's say, for example, don't do this experiment at home, okay? It's going to hurt a lot. You have a wall, and you have a car. Moving this way, of course, to the wall. And let's say, for example, go back to my original example, which is kind of easy problem, 11 miles per hour, okay? And you would want to stop it. Well, if it hits the wall and the wall is immovable or practically doesn't move, I mean, you can break a little if you want to, the car will come to a standstill, for example, in 1 second, okay? Bang. So in this case, the change in momentum is the same quantity. So the change in momentum, remember, it was moving 11 miles per hour, which is 5 meters per second. That's the initial example. And the car is 2,000 kilograms. 1,000 kilograms, 1,000 kilograms. So its final momentum is 0. The initial momentum is, so no brakes. You're not using brakes. You just don't do this at home. You're going to damage the wall and you're going to damage your car. Okay? You may even damage yourself. Don't try this, okay? So again, minus 5,000 kilogram meter per second divided by 1 second, this results in negative 5,000 newtons. Okay, it's a lot of force. Let's do the same experiment now with the same car, theoretically, of course. Okay, but instead of having I have a large amount of hay in here, okay, and I have the same car in here. Moving with the same speed, 11 miles per hour. Okay, 5 meters per second, and it's the same mass, 5,000. But instead, it goes through the hay in this case, displacing it, and each amount of hay it displaces slows it down. And let's say, for the sake of arguments, it takes about 10 seconds to stop it. Okay. Now, how much force is needed to stop this thing? Well, the momentum is at the end when it comes to a stop is still 0. The initial momentum is still 5,000. So how much change in momentum? It's 0. At the end, it's 5,000. I mean, at the beginning was 5,000. So the end is 5. But now it takes the whole 10 seconds to stop this car. Okay. So how much force is needed now? Well, negative 5,000 divided by 5 is negative 500 Newton. Okay. So at the end of the day, the hay will apply less force to stop the car than the wall, which means there is less damage to the vehicle. So there is less problems with the vehicle, and like the initial one, which has far more force, that could cause a lot of damage to the car. As a matter of fact, hay could probably take more time. You could take probably like half a minute, 30 seconds. So if it's 30 seconds, then you're talking about a ridiculous amount of a lot less. So if this is 30 seconds, so you're talking only if you have a little over 100 Newton. So if it takes half a minute, so let me find the number again. In the calculator, I always tempted to move to the other calculator, the other keyboard, I'm sorry. So it's about 167. 167 Newton, which is a very, very, very small force compared to 5,000. So it's not going to do much damage. Maybe you will have some scratches here and there on the vehicle, and that's it. So, so that's another example. So what matters in this case is the change in momentum over time, and that is the force. So the force and time play a major role together too in this combination. So the change in momentum is the impulse, and the impulse is force times time. So if the time is high, the force is low because the change is the same. Give it more time, then less force will result in the change in momentum. If the time is low, let me probably use a different color. If the time is less, so you would want to achieve the same effect but in less time, then you require more force. Really, that's all there is to it. So if the time is less in this case, well, the force needed to do the same thing is higher. So that's a concept of the impulse. So this is where the origins of the impulse are. That's the impulse. And this is the change in momentum all the time. Okay, so the change in momentum is always related to this concept. Okay, this is the concepts that are discussed in this unit, okay, in this chapter, I should say. Next week, we're going to briefly basically introduce or discuss the concept of energy. I know we did it in the lab on Monday, because the lab on Monday was about energy. So we're going to delve into it conceptually on tomorrow. I mean, sorry, not tomorrow, next week, actually. In the lab, if you guys remember, we were calculating the kinetic energy and the potential energy. We're going to discuss this concept in detail. One of the key things that the book delves in extensively, and please do not take it for more what the book is saying, is trying to come up with some sort of an explanation for what it means to have a gravity, the force of gravity, what is its meaning, and so on and so forth, and the fact that we don't know its meaning. Well, we know exactly what these things are, okay? Anything you can measure in the lab, you know exactly what it is. You define it, you measure it, that's its nature, that's the extent with it. There is no philosophy behind it, trying to see some sort of a hidden, some sort of a strings attached to the force of the gravity going from one end to the other, no. And if you can go in the lab and measure those quantities, namely the mass of one object and the mass of the second object and the distance between them, and relate that to the mass times acceleration through a spring, for example, which is properly calibrated to measure forces, then you're in good shape. That's it. That's all the extent with which to do. That's actually what Cavendish did when he measured the value of G, actually, the weight of the Earth also. So that's a famous experiment that Cavendish did, and I think it's mentioned in the book. So the point being in here, I'm trying to say in physics, we really don't delve into philosophy at all. We just take the values, define them, measure them. And if you can measure it, it's physics. If you can't measure it, it's just fantasy. It's any other thing. Like the concept, for example, of, I don't know, law, for example, or hate. Those concepts, they are not measurable in physics, so they're not physical concepts. They may have a different meaning somewhere else, but not in physics. So that's really some of the stuff I wanted to mention about that, because I was looking at the notes and did not really ring too much of a sense in there, okay? So you have the concept of gravity, we have the concept of collisions, momentum, and I know I mentioned briefly the angular momentum because this class doesn't really go into a lot of details about rotational motion, but in a similar fashion to linear momentum, you have angular momentum. A case that comes in mind, for example, is the ballerina. If you have had an experience, if you have had a chance to see a ballerina, for example, whether live or on TV, you will see how they spin, basically. If the ballerina has her hands both extended and spinning, and then brings them towards herself, she will go faster. She will spin faster. Her speed changes. She will be moving with a faster speed. She will cover more angles in the same amount of time, which is called the angular velocity. So the angular velocity will increase. And at the same time, if she was moving fast and then opens her hand, then in that situation, her speed also decrease. Her angular speed, the speed with which she's spinning, will also decrease. So this is what is known as, in this case, it's going to be an angular momentum. What the momentum in this case is how much mass you have, and how it is distributed with respect to the axis of rotation. In the case of the ballerina, she's spinning, for example, on her body. So that is the axis of rotation. If she brings her hands far away, then the mass is distributed far away from the axis of rotation. If she brings her hands closer, then the mass is distributed up to her, closer to her axis of rotation. So it's the same mass. The ballerina doesn't carry all of a sudden stuff. Although if you do increase the mass also, that is going to change the angular momentum at the end of the day, because it's mass and how it's distributed and how fast the object is spinning. So there's three concepts in here. And just like the linear momentum, angular momentum also is a vector. So when the solar system starts to form initially, and that's how we believe all of the extra basically solar exoplanets basically form, and other stellar systems, if you wish, form. So you have a cloud of gas that was left over from previous basically star that exploded in the past, like the case of the sun. And that gas, because of the force of gravity starts to coalesce, come together closer and closer. In doing so, the angular momentum now is conserved because there is nobody spinning or controlling the spin of the gas. So in this case, the angular momentum is conserved. So whatever angular momentum you started with is the angular momentum at the end when the solar system formed. So that requires that the vector is conserved and also the quantity is conserved. The vector is conserved requires that the planets, first of all, orbit on the same plane for the ecliptic, and the second also is the fact that the ecliptic, the paths meet a certain requirement. Okay, actually, they meet a certain requirement is a combination with the energy also, because again, similar fashion, and this is a concept we're going to explore next chapter. When the solar system formed, it had an amount of total energy, namely potential energy, because the parts of the solar system are far away from each other. So, but then as they come closer and closer, they lose that potential energy. Similar to the fact I demoed in the lab, and I know Alex basically mentioned the fact that I used the wrong word. I said the pen, but I was holding a marker. So if I drop, now I'm holding a pen, okay? So, so if I drop a pen now, I have potential energy. How do I know that? If I drop it, it gains speed and falls, okay? So it converts that to kinetic energy. Same thing with the solar system or any stellar system out there. So as particles come closer and closer, it's losing potential energy, meaning if the kinetic energy is going up, and if the kinetic energy is going up, that means the temperature is going up, the solar system. I mean, the objects that become closer and closer. But forget about the temperature component that plays a role actually in how the stars are fueled. The point being in here, they move faster and faster as they come closer from the center of rotation. If you go, for example, in the bathtub, for example, you fill it to a brim, and then unplug the sink where the water goes through, you will notice that the water starts to spin. And if you put a rubber ducky, the rubber ducky is far away from the sink is going to move slower than when it's closer from the source, from where it's supposed to go. Again, it's going to move faster on the other side. So that's exactly what Newton's laws are, and that all of it has to do with the angular momentum. Granted that the angular momentum is not required for this class, but I'm trying to connect it with the work of Mr. Newton, because Mr. Newton really based all of his discovery based on the laws of Kepler, and he explained them in this fashion. And he went, as I said, a step further by determining that that coefficient is actually the mass of the sun, and taking that and actually measuring the mass of other planets, for example. That's how we measured also the mass of Jupiter and the other planet out there. And even in binary systems also is the same law, to find the mass of the different components of a binary system, like two stars spinning around one another. And so it has applications a lot in astronomy, but also one of the complications that in astronomy also immediately was a consequence of Newton's work, far beyond what Mr. Kepler has done, and that is to predict when the next time Halley's Comet is going to come. And later on, for a lot of other things, among other things, the discovery of Neptune was based on this laws. So again, a theory, and this is a very, very important point I'm trying to drive in here. Theory in physics, if all it does is explain what has been observed, like the case of Kepler, for example, being explained by Newton. So if all it does is explain Kepler, that is not good enough. It has to go a step beyond. And that is the moral of the story. So if anybody comes to you and give you an explanation of some stuff in physics or whatever, okay, that sounds good. I'm going to come up with a million explanations for whatever I see. Is it useful? Can I make some consequences with it? That is the point. Okay. On that note, before I forget, I know we had a discussion also on Monday on a couple of problems in the homework, and those two problems, if you guys remember, dealt with problem 55 and problem 64. No, those problems are required for the homework for this week. And again, they are part of our preparation for the next exam. The next exam is not going to be next week, but the week after, because I'm still working on the review. Thank you.